Welcome to the Deep Dive. We're the show that takes all that information swirling around out there and really tries to boil it down to what's essential, what's fascinating, just for you.
Yeah, exactly.
And today, we're heading out there. We're talking about a dream that's, well, it's as old as humanity itself, isn't it? Making a home beyond Earth.
Right, not just planting a flag, but actually living there. So our mission today, you could say, is to really dig into what it actually takes to build permanent homes out in the cosmos.
Okay.
We're going to look at the incredible engineering hurdles, explore where we might realistically settle,
Right.
talk about the cutting edge tech that's making it possible, and crucially, the psychological side of things, living in these really extreme places.
Yeah, that human element is huge.
Right.
And we've pulled together insights from leading space architects, NASA's own plans, looked at some historical projects too, and even, discussions from people dreaming up these like future space cities. So it's a real deep dive into the where, the how, maybe even the who of building our cosmic future.
And how we're sort of fundamentally rethinking what home even means when you look beyond Earth.
Exactly. So let's start with the where. I mean, the moon always comes up first, right?
It does. It's the obvious first step. But building habitats right on the surface, it's exceptionally tough. The lunar environment is really unforgiving.
Yeah, I can imagine. It's not like just, dropping a modular home there, is it?
Mm-hmm.
What are the biggest immediate challenges, the stuff that makes it so incredibly hard?
Well, top of the list is intense ionizing radiation. That's a huge one. It means you need serious shielding. We're talking about burying structures under maybe 2 to 3.5 meters of regolith.
And regolith is that fine lunar dust and rock, right?
Exactly, that sort of pulverized top layer.
So you're literally burying your house under like 7 to 12 feet of moon dirt.
Pretty much, yeah. And then there's the thermal stress. It's extreme. You get these temperature swings, 500 degrees Fahrenheit, that's 260 Celsius between day and night. Yeah, that kind of cycling is brutal on materials, causes fatigue, complicates the whole structural design.
Okay.
And you've also got the constant threat from micrometeorites, even some larger ones. Macrometeorites, these are like tiny metallic bullets, potentially centimeters across, that could be catastrophic.
So it's genuinely dangerous. You need a whole different idea of shelter. And I guess that means not many windows.
Oh, absolutely. It severely limits fenestration windows.
Yeah.
And it demands materials that are just extremely rugged. So trying to erect buildings the way we do on Earth, it's really problematic.
Right.
And then there's the gravity, only 1/6 of Earth's.
Yeah, the fun bouncing part.
Right, sounds fun. But the long-term effects on our bodies, things like immunosuppression, muscle atrophy, bone density loss, osteoporosis, we still don't fully know. So designs might need to bake in artificial gravity somehow, or, maybe settlers would need to walk really long distances just for exercise.
So, okay, living on the surface sounds kind of grim, actually, like these compartmentalized bomb shelter type things, buried deep, hardly any windows, basically man-made caves.
That's a pretty accurate picture for long-term surface living, yeah.
And that sounds incredibly confining.
Yeah.
You get the protection, sure, but psychologically?
Yeah.
Is there another way, a way to get that safety, but maybe, I don't know, more space?
Well, yeah, that's where this more radical idea comes in. Going under the surface, specifically using natural lunar lava tubes.
Subsaline development. Okay, now that sounds like proper sci-fi. What are these lava tubes exactly?
They're basically thought to be old channels where lava once flowed billions of years ago. Parts of the roof collapse, but other sections are intact, forming these long underground tunnels or caves. They're subsurface, so you don't usually see them from orbit unless a part collapses, forming a skylight. But if you can find and access an intact one, well, they offer some massive advantages.
Okay, I'm intrigued. What kind of advantages are we talking about? Game-changing ones.
I think so. First off, natural protection. The roof overhead estimates are maybe 40 to 60 meters thick. That's incredible shielding against radiation and meteorite impacts. Way better than a few meters of regolith.
Wow, okay. 40 to 60 meters of rock.
Yeah. They reckon it could withstand impacts like several tons of TNT. And inside, you get this remarkably stable environment. It stays at a pretty constant minus 20 degrees Celsius.
So no more wild temperature swings.
Exactly. It moderates those thermal extremes, which is much easier on materials, reduces fatigue.
So it's like this giant, pre-built, shielded, climate-controlled bunker. But I've heard they're potentially enormous, right?
Oh, they're vast. We're not talking about small caves. Lunar gravity means these things could be huge, maybe hundreds of meters wide, kilometers long. You could potentially fit entire towns inside.
Whoa.
And that's not just technically useful, it's huge psychologically. Imagine having that sheer volume, that sense of space, after potentially being cooped up. It avoids that prison-like feeling. That's massive for long-term well-being.
Yeah, absolutely. And what about actually building inside them? Is that easier?
Potentially, yes.
Right.
Less danger for construction workers, maybe even shirt-sleeve conditions for some tasks eventually, meaning no bulky spacesuit. And you've got direct access to solid bedrock for foundations, for heavy equipment.
And being underground, protected.
Yeah.
Does that mean you can use different building materials too? More options?
Definitely. Suddenly, a wider range of materials and methods look viable. You could potentially use masonry, just, unprocessed moon rock, which is obviously abundant.
Right.
Or concrete made using lunar materials, maybe calcium cement to pour that for big structures, floors, or reinforce it. You could even think about fused structures, sort of melted in place without needing water or containing atmosphere. Useful for sealing surfaces.
Living off the land, but underground.
Pretty much. And things like inflatable structures become really interesting inside a lava tube.
Ah, okay, let's talk about those. Inflatables, we hear a lot about them. How do they fit into the picture, both on the surface and maybe inside these tubes?
Yeah, inflatable or expandable habitats are a really hot area right now. Huge potential for exploring the whole solar system, really. The idea itself isn't brand new, though.
No.
No, back in the 60s, NASA had Project Echo, these big Mylar balloon satellites used for communications.
Right, I remember seeing pictures of those.
And then Soviet cosmonaut Alexei Leonov, his famous first spacewalk in '65, he used an inflatable airlock, though apparently his suit got so stiff he had real trouble getting back inside. Had to let out some air.
Yikes. That sounds terrifying. But the tech must have come a long way since then.
Oh, dramatically.
Yeah.
In the 21st century, you had Robert Bigelow's company, Bigelow Aerospace. They did pioneering work. They launched those Genesis modules, free-flying prototypes, and most famously, the BEAM module, the Bigelow Expandable Activity Module. That's been attached to the ISS, the space station, since 2016. Still there.
Wow, so it's actually being used, tested long-term in space right now. What fabric did they use for that?
They use something called Vectran. It's a high-performance fiber, actually stronger than Kevlar in some ways.
Okay. So who's pushing this inflatable tech forward today? Any specific companies?
Yeah, several key players. There's Max Space. It was co-founded by Maxim de Jong. He actually designed the hulls for Bigelow's Genesis modules.
Oh, interesting connection.
Yeah. They're aiming for a first mission in 2026. And they have plans for habitat scaling up from like 20 cubic meters to maybe 1,000 by 2030. And they're even thinking about massive 10,000 cubic meter structures launched by Starship or New Glenn, perhaps.
And 1,000 cubic meters. That's enormous.
Huge. Then you've got Sierra Space. They're developing the Life Habitat Large Integrated Flexible Environment. It's designed as this 3-story module about 27 feet across for 4 astronauts. Lots of room for science, exercise, medical stuff, even a greenhouse.
A greenhouse and an inflatable. That really speaks to long-term living. Anyone else?
Lockheed Martin is also in the game. They're testing inflatable concepts, too, focusing on getting more volume for less launch mass. They've been doing these long-duration creep tests on Vectran material, basically seeing how it holds up under pressure over time. One test unit apparently passed 1,500 hours without failing, way beyond its target.
That's encouraging for reliability.
Yeah.
So where do inflatables fit best? Are they mainly for bigger standalone stations or?
Well, Brent Sherwood, a space architect, made an interesting point. He suggested their niche might not just be about making big modules even bigger. He sees them as potentially really useful as, like, connector elements on surfaces like the moon.
Oh, how so?
Well, they can flex and adapt. They could connect modules that aren't perfectly aligned or are at different floor levels. They can accommodate thermal expansion and contraction from those big temperature swings. So they could simplify the overall system design.
Ah, okay. So they offer flexibility in connecting rigid structures, too. Makes sense. So I've got surface bunkers, underground lava tubes, inflatable modules. But what about the truly grand visions, the, spinning space stations from classic sci-fi? Like O'Neill cylinders.
Ah, yes, the O'Neill cylinders, the Island 3 concept. Now we're talking truly ambitious third-generation space colonies.
Third generation. And the scale is just immense.
Absolutely immense. The classic design is a pair of cylinders. Each one is maybe 20 miles long, 4 miles in diameter.
20 miles long.
Yeah. Spinning to create artificial gravity. Together, they'd provide something like 500 square miles of land area inside. Enough space potentially for several million people.
Several million. That's not a station, that's a whole new world. What would it even look like inside?
Imagine looking up and seeing the landscape curve up and over your head, kilometers away. The design has these long strips of land alternating with huge window panels. Outside, you'd have giant mirrors angled to reflect sunlight inside, opening and closing to create a day-night cycle. Some concepts even talk about having clouds form naturally at around 3,000 feet altitude, maybe even user-controlled weather or seasons eventually.
That's incredible. But surely there are debates about how you'd actually build and manage something like that.
Oh, absolutely. Lots of discussion about how to optimize the internal infrastructure. Do you need thick layers of soil for farming or just for shielding? How do you distribute power efficiently across such a huge area? Some argue for keeping infrastructure accessible, not burying it all underground, while others think underground service tunnels are safer and easier to manage.
Fascinating debates.
Yeah.
It really shows the level of detail people are thinking about, from the grand vision down to, like you said, where the pipes and wires go.
Exactly.
But none of this, whether it's a buried moon base or a giant spinning cylinder, none of it works unless you can, well, live off the land, right? Use what's already there. Which brings us to ISRU.
Yes, in situ resource utilization, ISRU. It's absolutely fundamental. It means, finding, collecting, processing, storing, and using materials that you find or make right there on the moon or Mars or wherever.
And why is that so critical? Just cost?
Cost is a huge part of it, yes. Launching everything from Earth is incredibly expensive. But it's more than that. ISRU is what allows you to reduce dependence on Earth, to enable a truly sustained human presence, maybe even build a real space economy eventually.
Okay, so what kind of resource quantities are we talking about? Is it enough to make a real difference?
The projections suggest yes. For maybe a single lunar lander mission, you might aim for, say, 30 to 60 metric tons of useful stuff extracted.
Okay.
But scaled up, for activities in cislunar space, Earth-Moon space, you could be looking at hundreds, maybe thousands of metric tons per year. And for sending humans to Mars, perhaps hundreds of tons annually just for propellant.
Wow, those are significant amounts that really could support long-term infrastructure. Is NASA pushing hard on this?
Very much so. They have their Lunar Surface Technology Demonstration Strategy. A key goal is boosting the readiness level for technologies in ISRU, but also related areas like power, autonomy, robotics, excavation, construction. They all tie together.
Makes sense. And are they working with others on this? It sounds like a massive undertaking.
Definitely not doing it alone. They've fostered the Lunar Surface Innovation Consortium, the LSCC. It's this big alliance, universities, industry partners, nonprofits, NASA itself, other government agencies, all collaborating.
Okay.
Within LSE, there's a specific ISRU focus group, maybe 200 or so experts involved. They're working to define key goals, like how do we efficiently extract oxygen and metals from regolith? How do we prospect for water ice? How do we make systems modular and interoperable?
So they're tackling it from multiple angles: water, metals, oxygen.
Right. It's kind of a dual path approach. Focus on mining water ice, which is crucial for life support and rocket fuel, but also focus on extracting oxygen and metals directly from the dry regolith, the rock and dust, which is vital for building materials and, again, breathing air and propellant.
And NASA's role is sort of fostering this, providing support.
Yeah, they see their role as enabling industry to lead the development. NASA provides fundamental research, access to testing facilities, shares information, basically trying to lower the barriers so companies feel confident investing in developing these ISRU systems.
Got it. So what are the actual nuts and bolts? What are the key work areas within ISRU? What does it actually involve doing?
Well, broadly, you've got a few key steps. First is resource acquisition, isolation, and preparation. That's your drilling, digging, scooping, moving the material around.
Okay, the mining part.
Essentially, yeah. Then comes resource processing. That's using chemical processes, heat, electricity, maybe even biological methods to convert the raw materials into something useful mission consumables like water or oxygen or feedstock for construction.
Like raw materials for 3D printing.
Exactly. So specific areas include water and volatile extraction, getting metals out of the regolith, creating that construction feedstock, but also things like supporting food production, processing waste, maybe even making plastics from waste streams. It's really about building a whole industrial ecosystem in space.
A circular economy, like you said. And how are they testing these ideas, getting people involved?
One really cool way is through public challenges. NASA runs these competitions to engage universities, companies, even citizen scientists.
Oh, yeah? Like what?
There's been a bunch. The Space Robotics Challenge, focusing on autonomy. The CO2 Conversion Challenge, trying to turn carbon dioxide into sugars, potentially for food or biomaterials. Watts on the Moon for power systems. Break the Ice for digging up icy regolith. The Lunar Dust Challenge dust is a huge problem.
I bet.
Yeah. Plus the Moon Mars Ice Challenge, Lunabotics for student robotic mining, and the 3D printed habitat challenge, which got a lot of attention. People designed and printed subscale habitats using simulated Mars dirt.
That's fantastic. Getting lots of minds working on these specific problems.
Mm-hmm.
And you mentioned earlier, some of this tech might actually help us back here on Earth.
Absolutely. There are definite terrestrial synergies.
Yeah.
The whole philosophy behind ISRU, reduce, reuse, recycle, repair, reclaim, that's directly applicable here.
How so? Specific examples.
Well, think about construction. Developing 3D printing techniques that don't rely on Portland cement, which is a huge source of CO2 emissions that could be big.
Right.
Also, advances in remote operation and automation needed for space, have applications in mining, disaster response, lots of areas here. More efficient power generation and storage, boosting renewable energy use, better water purification techniques, improved methods for growing food in closed environments.
Yeah.
It all feeds back.
That's a great perspective.
Yeah.
Pushing boundaries out there helps us innovate right here. So, okay, we've covered the where the moon, maybe lava tubes, maybe giant cylinders. We've covered the building materials, the ISRU. Now, maybe the most crucial part, the who, the humans.
No.
How do we support the people who will actually live in these distant extreme environments? What are the challenges beyond just the physical?
Yeah, the human element is absolutely critical, especially the psychological well-being on these really long missions, months or years away on the moon or Mars.
It's not just a weekend trip.
Not at all. You're dealing with profound isolation, being confined in relatively small spaces, maybe with the same few people. Then there are the communication delays. Talking to Mars can mean a delay of up to 30 minutes each way.
Wow, 30 minutes. That kills any real-time conversation.
Completely. Add in microgravity effects, living in this inherently hostile place where a mistake can be fatal. It all adds up. These factors can easily lead to stress, anxiety, depression, reduced cognitive function, and that can seriously jeopardize the mission.
You can't just, like, video call your therapist on Earth if there's a crisis with that kind of delay.
Exactly. Traditional psychological support becomes much, much harder. So
Okay.
they're developing innovative, proactive solutions.
Like what? Preparing people better beforehand.
That's a big part of it. Really intensive pre-mission training, resilience training, working on team dynamics, giving astronauts a toolkit of psychological coping strategies before they even leave.
Okay.
And then in-flight routines are key. Things like mindfulness exercises, relaxation techniques, deep breathing, progressive muscle relaxation. These have been tested in places like Antarctic research stations, which are good analogs for space isolation.
Yeah.
And they're proven to help reduce stress, improve focus, help regulate emotions. Plus, they're non-invasive. Astronauts can do them themselves.
Yeah, that makes sense. Using techniques proven in other extreme environments.
But what if someone needs more, like immediate help and mission control is minutes or hours away via comms?
That's where automated psychotherapy comes in. It sounds a bit futuristic, but it's seen as a really crucial tool.
Automated therapy, like an AI therapist.
Sort of. These are systems designed to provide confidential, on-demand support 24/7. They can offer things like cognitive behavioral therapy, CBT, tailored specifically for the stresses of spaceflight.
They could guide an astronaut through exercises to manage anxiety, deal with feelings of isolation, work through conflicts right when they need it without waiting for Earth. It gives them immediate access to support.
That's incredible, really prioritizing mental health as a core mission requirement.
Yeah.
Okay, that's fascinating for supporting humans within engineered structures. But I heard you mention something even more radical earlier, something about living habitats. What on earth is that?
Yeah. This is definitely out there, but it's a concept people are seriously exploring. The idea is, what if the habitat itself was, in part, generated by life? Non-sentient life, like microbes or fungi, creating a self-sustaining ecosystem that is the structure.
Whoa, okay, so the walls would literally be alive? How would that even work? How could biology handle, say, holding in air pressure?
Well, think about biological materials. Some bioplastics or biominerals, like the calcite shells some organisms make, they can actually maintain pressure differences, maybe a few kilopascals. That's
Oh,
similar to blood pressure in a tall animal or gas pressure inside seaweed fronds, with wall thicknesses of maybe just a few centimeters
a
potentially.
few centimeters of living material holding back the vacuum.
Yeah.
And what about temperature? Space is freezing cold or boiling hot.
The idea there's something like a solid state greenhouse effect. You'd have translucent biological layers, maybe like silica aerogels, which some organisms like diatoms actually work with on a nanoscale.
Diatoms, so like little algae.
Exactly. These layers could let visible light through for photosynthesis inside, but trap heat, infrared radiation, potentially maintaining Earth-like temperatures, maybe 15 Celsius, even way out near Jupiter.
That's amazing. And stopping air leaks, that's always the big challenge.
Right. The concept suggests habitat walls made of materials with very low permeability. They could potentially inhibit gas loss so effectively that a habitat might stay pressurized for like 13,000 years for a 1 centimeter thick wall on a 10-meter habitat.
13,000 years.
Yeah.
That's geological time.
It's a theoretical calculation, but it shows the potential. And the ecosystem inside could help too, maybe by converting volatile gases into heavier molecules that don't escape as easily.
Okay, mind blown. What about radiation and getting nutrients?
For radiation, compounds like amorphous silica or reduced iron, biologically produced, could block harmful UV without blocking the visible light needed for photosynthesis inside. And there's plenty of solar energy, even far out, nutrients. Well, asteroids and comets have the essential elements. Studies have shown microbes can grow on meteorite material.
Aye.
So you'd need a closed-loop ecosystem inside, probably compartmentalized to process waste and recycle everything.
So what's the ideal size for these living habitats, and how does this compare to something huge like terraforming Mars?
The model suggests something around a 10-meter radius might be optimal with those thin walls, maybe 0.01 to zero point 0.1 meters thick. And they'd need ongoing maintenance, but through biological growth and regeneration, recycling the wall materials, maybe absorbing new stuff from local regolith if needed.
It's like gardening your house.
Kind of, yeah. And interestingly, silicon might end up being really important for carbon-based life in space because it's so useful for controlling temperature, pressure, UV. But the key difference from terraforming is huge. Living habitats are localized. They're biologically driven. They aim to adapt to the environment, not change the whole planet.
Ah,
They're potentially much more sustainable, less resource intensive, and pose minimal environmental risk compared to terraforming, which is global, incredibly expensive, and fundamentally irreversible. It's a different philosophy.
wow. Okay, this whole deep dive has been fascinating. It really shows how everything is connected, doesn't it? The engineering, the resourcefulness, the biology, even our own psychology. It's all part of charting our course out there.
It really is.
From finding caves on the moon to imagining these giant spinning cities, making building blocks from moon dust, ensuring people stay sane light minutes away, it's this incredible tapestry of innovation. And it really makes you rethink what home even means.
Definitely. The challenges are just enormous, but the creativity and ingenuity being applied are equally vast. It's not just about surviving out there, it's about finding ways to actually thrive, creating environments that support human life in the deepest sense.
So here's something to think about as we wrap up. As we keep pushing these boundaries, where we live, how we live, what are the unknowns? What unforeseen biological adaptations might emerge in these living habitats, perhaps? Or what new psychological hurdles will we face in these cosmic homes? And how will that fundamental human drive, that need for both comfort and adventure, ultimately shape these dwellings among the stars?